So my name is Danielle, and like Glenn said, I'm here at JPL for a few months, and I'll tell you a little bit about what I'm working on, but that will be in a little while. So mainly I'll be talking about digitally enhanced interferometry, which was a technique that was developed at JPL and some of the first experiments done there. And then when Daniel Wucenich moved back to Australia, he made all of his graduate students work on it. So that's, all of these people here mainly are people in Australia, with a few people here. A brief overview of what I'll be talking about. We'll discuss heterodyne interferometry and shortcomings. Then we'll talk about digitally enhanced interferometry. And I'll talk about some experiments that could benefit from using digital interferometry, or some that either have already benefited or could benefit. And then, so this will include lock acquisition for LIGO, optical-bench simplifications for LISA, an optical phased array, which is what we're working on at JPL, and some frequency noise reduction in fiber sensors. And then the last little bit of my talk, I'll talk about the next generation for digital interferometry and looking forward. So in conventional heterodyne interferometry, for those of you that aren't familiar with it, we have two optical fields that are at slightly different frequencies. So I've illustrated them here with a red and a blue lines. And you can see that they, in here we have an acousto-optic modulator that's shifting the frequency of the light. And so at the photodetector, we would get something that looks like this green trace that's proportional to the difference frequencies, I guess. So you have this cosine term here that's oscillating at this difference frequency. And so in heterodyne interferometry, it's all about measuring the phase of this beat note, is what we call that. And so all of your optical path length information or any scattering or anything will contribute to this, to the phase of this signal that you measure. And so there's a lot of people that have been working on something called a phase meter, and that's to extract the phase of this signal. I won't really talk about it that much. If you have some questions, I can answer at the end. But just assume we have something that gives you a perfect, recovery of whatever the phase of this signal is. So the other interesting thing about heterodyne interferometry is that when you have a one wavelength shift in one of the optical fields, so something that's even on the optical wavelength of a micron or even sub-micron shift here, you would get a full wavelength shift in the optical in the heterodyne beat note. And so you're translating really, really small displacement signals into a big thing that you can measure maybe at radio frequencies with your detectors. And so this is why heterodyne interferometry is so powerful, because you can get this high sensitivity using optical wavelengths. So the problem, though, is when you have multiple either scattering sources or multiple elements that you're trying to measure, when we look at the detector, say we have reflections off of 3 mirrors, and we were to look at the detector here, the net effect of all of these phasors adding together basically gives you something that doesn't really look like a nice sinusoid. And that's okay, but usually you don't want that in heterodyne interferometry. You want to look at one thing and you want to measure the phase very carefully. And so you lose all that information basically when you get that vector sum of all of those phasors that come down to the detector. You lose all of the individual, individual information from each mirror, effectively. And so that's what digitally enhanced interferometry, or DI, targets, is getting rid of this problem, I guess. And so all you do is essentially add an electroactive modulator. And in our experiments, we're using these fancy fiber-coupled integrated optic waveguide modulators, and they have really high like gigahertz bandwidth, maybe even like 10 plus gigahertz, and pretty low insertion losses, and also really, really low VPIs as well, so maybe less than 10 volts even. And this will produce a phase modulation, and you modulate the phase of the light with a pseudorandom noise code. And so it's a funny looking thing like this, and if we were to only focus on what that would look like at the detector, basically if we have just one mirror, let's say, and you do this PRN phase modulation onto the light, you get something that looks pretty gross. And essentially then, if we were to add in all of these extra mirrors, and they've all also still have this phase modulation on it, you get even something that looks worse. So that's when the digital signal processing part comes in. So you optically completely mess up the light, and then you are going to basically try to undo everything that you did in signal processing. So I'll explain that in a cartoon, easy way. You have your, if we turn the modulator off, or if we didn't affect it at all, you'd get your normal heterodyne signal. When you apply the PRN encoding, you're shifting the light by 0 or pi radians, or 180 degrees or 0, which is happening at A. And B, that's what we would detect, and then the photodetector is like a chopped up sine wave, basically. C is if we now do the signal processing appropriately, what we want to do is multiply this detected photodetector signal by a delayed copy of the code. So we basically just want to undo what we did to begin with, and if you do it right, you get your heterodyne signal back. If you don't do it right, let's say here now we still have the same signal at the detector, but say we use an improper demodulation delay. So say we just don't tune the delay, electronic delay quite right. We get something that looks again like a chopped up sine wave. So this seems like a lot of work for nothing. If you do something right, you get back what you originally had. But the benefit is that you are able to multiplex signals, and you get a strong rejection to unwanted or to scattering effects. So I'll explain this in another experiment. This is essentially the exact same experiment that you saw before, but in fiber. And I'm using this one because I have results on this experiment. So essentially you have, again, you have a laser that's offset phase locked, or again just with a offset phase lock to another laser to give you a heterodyne signal at the detector. Light from the signal laser comes through the electro-optic modulator, gets modulated again. Some of the light gets sent down to these fiber connectors. So you can think of each of these maybe as your target mirrors or something. And we used ultra-polished connector mirrors, not the angle polished, but the flat ones, so you get a bigger reflection. So essentially we were monitoring the back reflections from each of these signals, but again, we have this funny modulation on there. And so all of these little reflections come back and are detected at the photodetector. So if we wanted to monitor length fluctuations in length 1, for example, we could take the phase that we measure using this fancy phase meter, for example, the phase of the reflection from R1 and the phase of the reflection from R2 using different delays. So you still only have one photodetector, but if you apply different demodulations, you can get something that you can combine together in a measurement to give you, for example, the total path length fluctuations between these 2 points. So this tells you the displacement noise, I guess, in L1. And so you only need one modulator and one photodetector. All of the rest of it stays the same, but you can now recover multiple interferometric signals just by using one detector. So that in itself, the signal multiplexing is really great. Sorry, is this going? So to actually see that it was working, we modulated 3 different lengths of fiber. We did a square wave with just a PZT fiber stretcher, a sawtooth, and a sine in length 3. And sure enough, if we measured each of these reflections from each of these 4 points correctly, we could recover all of the data without a problem. So this is just real-time simultaneous sensing of these 3 different fiber lengths. I will come back to that in a little while, but first let's just talk about then what the big advantages of a system like this would be. First is spurious interference rejection. So parasitic interferometers scatter light sources. This can be a huge problem in heterodyne interferometry, trying to get rid of any of these problems. Another thing is electronic crosstalk. You get a really high common mode rejection of several noise sources through a single measurement chain. So if you were using multiple photodetectors or different ADCs, you could have ADC sample jitter, or you could have phase delays due to thermal fluctuations of your cables or something. Because you're using the same detector and going through all these different things, when we would do like a difference measurement, for example, reflection 2 minus reflection 1, all of these things are common throughout the whole chain, and so you can strongly reject most of these, which is great. And the other thing is that the complexity really moves from the hardware to the digital signal processing. It's not necessarily trivial, but the hardware itself becomes simpler now. You don't necessarily need lots of optics or lots of detectors or things like this. Another thing that's been really good is just the miniaturization aspect. So everything suddenly gets more complex, more compact as the complexity of the hardware decreases, the compactness can also, you can start really looking at compact systems. So this was the original thing, experiments that were being done at JPL when they first developed this technique. So how you can replace an optical head or something quite big with something a bit smaller. So here you would have, let's say, a partially reflective surface. So some of the light would scatter would be reflected back toward your detector, and then some of it could go and probe like a target retroreflector or something. And so now you have these two measurements that you need again to get the displacement between these two. So one thing that we should talk about too is the length separation. So there's, depending on how quickly you modulate will tell you how far apart these two have to be. Another way of thinking about this is how quickly or how far has the light traveled before you apply the next chip in the PRN code. And so if you are doing something in reflection, if you remember back to this experiment, it's looking something like this. If we're trying to monitor basically the distance between these two, that will be related by how quickly we're actually applying the PRN modulation. And so you get, and if you're doing this in reflection as opposed to transmission, you get this additional factor of 2 because it has to travel there twice. You get the round trip there and back. And so with something like 100 megahertz modulation, you would get 1.5 meters between these two. Which is still quite big, but later I'll tell you how we're working to get that down. The other initial experiments that were done was to compare the readout with something we know, which is Pound-Weaver-Hall locking. And so this was an experiment done at ANU where you lock a 4-meter long cavity using Pound-Weaver-Hall locking. So you basically lock the laser to the cavity, or sorry, to the cavity to the laser, and then you read out the displacement noise using the digitally enhanced interferometry technique. So you would again monitor. The way that you do this is we're monitoring the two signals in transmission. So we monitor one beam that passes straight through the cavity and gets detected on a photodetector with the one that comes in, has one round trip, and then comes to the photodetector. So again, we take the difference of these two phase measurements to tell us the overall displacement noise of the cavity. And so comparing this, again, with, like I said, a Pound-Weaver-Hall technique, this gives us a upper noise, or an upper displacement noise, I guess, on the readout of this technique. And so you can see between, I don't know, about 1 to 10 hertz, you're about 5 picometers, which isn't bad. And then we can talk about some of these other things if you're interested. So the rest of my talk, I was going to talk about what other things it could be useful for. So we already know there is a simplification in hardware potentially. You can have picometer level resolution, displacement resolution. So what could we use this for now? So in my talk, I'll talk about lock acquisition for LIGO, like metrology and optical-bench simplifications for LISA, phased array, beamforming, shaping, steering, which would also, I think, be interesting for LIGO types for creating interesting beam profiles, and then fiber sensors and frequency noise reduction, and then, like I said, next generation DI. So first thing, lock acquisition for ground-based detectors. We always see these plots, the sensitivity curves of LIGO, but they only look like this if the interferometer is locked. And so if the interferometer is not locked, it's not a detector, and we can't get the things that we want. As we're moving to more complex systems, especially in advanced LIGO, it gets harder and harder to control all of these additional either mirrors or cavities or whatever we have, especially too as we're getting larger masses and weaker actuators. And so there's been a lot of talk of getting a deterministic lock for advanced LIGO, and there's already been a few plans for this. Most of them are based on Pound-Weaver-Hall locking, so which works really well. But the only problem is that you have a really short region where your air signal is linear, and you have to be. Well, maybe I'll get there in a second. So one way that you could potentially use digital interferometry in a lock acquisition scheme, whereas we do this single pass versus multi-pass cavity measurement again. Let's just say, so this is just for one of the cavities that we want to look at. So you compare the straight through versus the round trip phases, and you get information how to lock you can get an air signal over multiple free spectral ranges. So this is a comparison between a PDH air signal and between a PRN or a digitally enhanced air signal. And so you can see this one, you can kind of have full-time readout of where the optics are, and you don't have to be close to resonance. And I think that's a really important thing, is that you have these linear control signals, but you don't have to be, the cavity doesn't have to be anywhere near to resonance. So it would be a really useful tool for just knowing where you are. It might not have to be even the part that does all of the locking, but even just getting a readout of where everything is would be interesting. And again, this multiplexing capability allows you to sense multiple things at the same time. So it could be pretty useful. The other thing that would be good is that you can also, from this, so besides longitudinal control of cavities, you can also get angular information or wavefront sensing signals. And so now you can actually look at alignment fluctuations through the straight beam versus a round trip as well. And by using a quadrant photodiode, you can get information on tilt and offset. Again, using this digitally enhanced interferometry technique. So it's the same sort of readout, you just replace your normal detector with a quadrant detector. As far as LISA metrology goes, which is what I'm interested in, the LISA baseline pretty much requires passive stability of all optical components in the sensitive path. So it means build everything to picometer stability. And so if you've seen maybe some of these pictures of optical benches that we build, this is, they use these fancy bonding techniques to get everything to just be really stable on nice pieces of glass that don't change much or don't move much when the temperature changes. What if we could make it more simple? What if we could do something like what if we could implement the optical bench in as simple as something as a waveguide? And especially with all of the changes that LISA, or with all of the drama, I suppose, that's been happening with LISA recently, it is useful to have a think about some of these things. How much simpler could we make it? So do we really need passive stability of all these sensitive path lengths? And what if we could just measure all of them to picometer stability, and then do something with that? So this was something that I presented at the LISA symposium a few years ago, and it's really a primitive work. It's more of just a thought problem to see how simple could we make LISA with digital interferometry. So here, I've shown you there's supposed to be the 3 satellites, and so on one of these, all of these would be on one satellite. So we have 2 proof masses, 1 laser that's going to be going through our modulator, and then basically you can see we have a few fiber outputs on each of these. So one of them goes to monitor the proof mass location, one of them goes to go out to the distant spacecraft, and then we have the exact replica down there. So if we had some sort of bench like this for LISA, again, we still really care about, for LISA, we care about the proof mass to proof mass measurement. And the way that people in LISA interferometry do this measurement is, it's called like a strap-down architecture. And you get a proof mass to bench measurement, and then you do a bench to bench measurement, and then you get a bench to proof mass measurement. But really, you want proof mass to proof mass. So this is a similar measurement scheme where you would do sort of the same thing. You again do a proof mass to the bench using digital interferometry. So you could get this measurement and something that does this measurement. And I have a whole bunch more slides on this at the end if anyone was interested in seeing it. It's really just addition and subtraction of, if you measure the right things, you can subtract off noisy bits. So basically you can just measure it to picometer stability as opposed to requiring things to be sensitive to picometer stability. And if you measure all the right things, you can take out all of the length fluctuations and get something that's insensitive, or that gives you your proof mass to proof mass measurement. Again, this actually helps, this could help LISA a bit, because some of the problems in LISA interferometry, like the backlink fiber and the telescope backscatter, these are big issues for LISA, and this could potentially take care of that. The other thing is, like I said, the simplification of the optical bench. If you could get rid of that big piece of glass, you might have you could have significantly lower costs and perhaps a smaller spacecraft. And again, this could maybe be implemented on a small waveguide. Again, that's kind of just an early work. Don't jump on it too much. The optical phased array. This is now something that I've started working on with Glenn and Brent at JPL, and it's the idea. For a long time, people have wanted to do optical phased arrays, and phased arrays are not new technology. They've been used in RF frequencies for a long time, and the idea is that you have multiple emitters, or multiple emitters in an array. And you control the relationship of the phases in each of these emitters to give you some profile that you want in the far field. So in this case, you could control all of the phases of these to give you some constant phase front. In another one, you could give you some steering, or even like lens, or give it a lens-like effect. And so that's worked really well for, I guess, radio and radar, sonar, a whole bunch of other fields. But at optical wavelengths, it's so much harder. And the reason is that you have to control each of these. I guess there's two problems. One, you have to actively control the phase of each emitter. And any fluctuation on, because your optical wavelength is microns, anything even lower than that, any fluctuations like mechanical or thermal fluctuations will really corrupt that. So you have to measure it and you have to control it. So you have to do that for each one of these. So scalability is a hard problem. People have looked into optical phased arrays for a while, and a lot of people have done some proof of principle demonstrations in the lab. But usually these require each of these to have its own, its own beam splitter and photodetector. So a problem of scalability, so it's a big problem of scalability. Anyway, if you could, in theory, if you could come up with something that would phase all of these together and come up with good control systems to do this, it would be really useful for intercraft or intersatellite metrology, such as LISA or GRACE. Definitely for steering beams around. So if you don't even need steering mirrors, or if you don't have to actuate on anything mechanically, if you could just do everything just by controlling the phase, just by changing the interference properties between them, that would be really great. The other thing that you could do is, if you imagine that you seed each one of these elements with its own laser beam, you could potentially have a very, very high power laser beam, which might be interesting for something like LIGO types, where if we could get to really, really high power beams with this potentially. So again, the way that this works is one of these DI ideas. You have something that does your phase modulation. So this is our pseudorandom noise. This is our pseudorandom noise phase modulation again. We would split that into a whole bunch of different things. So however, let's say we wanted n elements in the array. So we split this into n channels, and then each of these comes to some common reference flat. So each of these would have to be referenced to the same plane if we want to be able to phase them in the right way. And so if you look at the back reflections of these, so most of the light we want to be sent out to the far field, but we just want a little bit of it to be reflected back so we can pick them off at the detector. Now we need these elements here to do phase control as well, so we can actually feed back. You could use fiber stretchers or something as well. But again, we want something, fiber stretchers start getting bulky as well. And so part of the development that we're doing right now is coming up with just basically taking everything that's in red on this diagram and making it in one integrated optical waveguide. So you take all of these bulky components and shrink them into something really, really small. And this is great for scalability. The other thing that we're after is something like an optical head design, basically something that gives you this common reference flat with multiple elements as well. So it's coming along pretty well. Right now we're setting up stuff in the lab just for just a steering in one dimension, just for proof of concept. But these types of things are really not so far off, and for making it quite small. So again, this can be used for steering, but also for beam forming. So creating arbitrary wavefront or arbitrary beams with particular wavefront characteristics that you might want, which would be useful again for LIGO. I mean, if we're thinking really, really far advanced LIGO, it might be interesting to think about if we had really high powers and could make kind of any beam shape that we want. How far could we push it, or how much would our designs, or what could we change? What could we simplify? So this is just a depiction of maybe doing the steering for GRACE 2, an all optical GRACE, and this would be just making either a high power beam for debris tracking, or if you can imagine if you created a high enough power beam, you could potentially compensate using your optical phased array. You could compensate for any atmospheric distortions already, doing your phased array on the ground, and maybe get high enough power so you could push space debris or something around as well. Another thing, I think I know this is a big mishmash of experiments. I'm just kind of telling you a whole bunch of different things, and if there's anything in particular that you want to know more about, ask me after. Another thing that our group works on is fiber sensors. And this is, back to this experiment, this multiplexing experiment I had presented before, is a frequency noise reduction. So if what we were doing here, I said, was monitoring each of these reflections to get displacement information for each of these fiber lengths. But really, that's only part of the story. Displacement information couples in, like a change in the physical path length would give you this effect, would give you displacement noise, but also laser frequency noise would mimic a similar effect. You don't know if it's laser frequency noise or if it's displacement noise. But in a system like you just saw, most of the light travels the similar path, and so really there's only one length. Like if we were looking from reflection 1 to reflection 2, most of the light takes a similar optical path, and so there's only a little bit that goes in an additional way that's not common. And so usually the way that we can mitigate laser frequency noise in LIGO or something is that we physically match the arm length. So any fluctuation in one path will be matched in the other path. Or another way that we can do it is that we can feed back to the laser's frequency to lock it to a reference. And these are both really good ways of reducing your susceptibility to frequency noise. In a system like this, though, if you measured the right length, you could combine them in a way that would give you a combination you could combine these lengths in a way that would give you a combination that's actually free from laser frequency noise. So this frequency noise term couples out, and you're actually only sensitive then to the physical length changes. This works decently well. Here in this plot, I measured one length and then did this combination of length 1 and length 2 like you saw in the math on the previous page. And really what you want to take away from this is, here's what happens if you measure the length and don't use any knowledge that you have from the other length, and here's what happens if you use knowledge from length 1 into length 2. And so you get a decrease, you get a drop in your laser frequency noise. And again, this is enabled because you have this multiplexed, these multiplex signals. You have more information that you can use to make a better measurement of the same thing. And so this was something that we did a few years ago. A postdoc in our group then took it one step further, and he not only used this type of fiber sensor PRN readout, but he also used now this in combination with time delay interferometry. And this was developed for LISA to cancel frequency noise. But you can also demonstrate it in a lab, and this is exactly what he's done. He has essentially a Michelson type interferometer. I'm sorry if you're not used to looking at these crazy fiber diagrams. They're not as pretty as free space. But here you have, here's your phase modulator that does your PRN encoding for your digital interferometry. We have then, it senses 2 different lengths essentially. These the light gets reflected and then combined with a local oscillator on the detector. And in the only addition, like I said, is he's done more post-processing, this time delay interferometry, to do an additional frequency noise cancellation. And effectively, what TDI does is it stimulates it emulates an equal arm length Michelson. And so even though the light didn't physically travel down the other path, if you can, in post-processing, combine it, you can make it look like it actually did travel down, and you combine the two together, you can get this combination that's immune to laser frequency noise, or quite immune to laser frequency noise. So here's a readout of the Michelson without using this additional post-processing, and here it is with using the time delay interferometry. And he got really nice suppression at lower frequencies. Next generation digital interferometry. So even though there's a whole mishmash of experiments that have been done, we're trying to see how much further we can go and how much simpler can we make it. Even though a phase modulator is not an uncommon thing to have in your lab, how much simpler could we make it? And is there any way we can, how much further can we push the limits, basically? And the way that we can do this is with a fancier modulation scheme called quadrature, based on quadrature phase shift keying. And in just a recap of what heterodyne interferometry does, you are using a frequency offset to essentially step you through a whole fringe or a whole wavelength. And so here the black is your I'm losing my train of thought. Here the black is just your beat note frequency at the detector, but the way that these phase meters work is that you compare it with another sinusoid that's running at the same frequency, and so you have kind of two components. You have the in phase and the quadrature component. And what you're doing in a heterodyne system is that you're actually just physically moving one with respect to the other to sweep out both of those quadratures, so you have information, constant information of everything that you need to know. And this works really well. The other way that you could do it, and this is what this next generation DI is to remove that requirement for having a heterodyne readout. So going to more Homodyne now based readout. So we've gotten rid of the AOM, or the frequency offset now, and we can actually jump through all the different quadratures, that we can kind of jump back and forth between quadratures using a phase modulator. So that's already what we had before. So we can use now this phase modulator to do two things. Not only apply the pseudorandom noise code for all the signal isolation and multiplexing, but we also use this to jump us to different points, basically to sample the I and Q the same way that the heterodyne does, but we don't necessarily need it to be doing it all the time. And you can still get phase recovery even without this local oscillator. And so one of the PhD students in my group is working on this, Andrew Sutton, and he's just getting first results. Basically, he has something that does the PRN encoding with the QPSK. So now it's a 4-stage modulation as opposed to the 2. Instead of just the 0 and pi, you have now 4 elements in the constellation. And then he sends this through essentially a ring fiber, and he uses an electro-optic modulator just to inject calibration signals. And then reads it out. Basically, everything comes back to the detector, and again, there's no local oscillator here. You're using your fancy modulation to step you through the right things. And he's recovered basically the first pass, so something that's come straight through, and then something that's gone around and around and around. And as you can see, multiple round trips have a higher displacement because they've traveled through the modulator more times. And this is all real-time information, or this is all information that he's taken. And sorry, most of this I think he probably did in post-processing, but the phase meter then gets suddenly simpler as well. So not only does the hardware not require you to have an offset phase lockulators or an additional AOM or something, but your phase meter is a lot simpler. It's not a fancy heterodyne phase meter anymore. The noise floor of this system that he just took was about 10 picometers. Which isn't too bad. This is at higher frequencies. If you can read the x-axis, this is 100 hertz. So in summary, we're making quite a bit of progress. We've done quite a number of experiments using this technique. The great advantage is that we're trying to transfer the complexity from hardware to signal processing, which seems like a good thing for space or for ground. We still have the potential for improved performance, and we're still continuing to push the limits. We want fewer components, faster modulation. Modulators that you can buy are the electronics and phase meters and stuff that we're developing in the lab right now are going from sort of 100 megahertz modulation to gigahertz, to maybe to 1 or 2 gigahertz. And it's not so far off. I mean, probably in the next year or so we'll have really good results. Pretty much updating we could update any one of these experiments with faster modulation, so everything gets smaller and smaller and smaller. So I have a whole bunch of slides on each one of these experiments if you had particular questions or just general questions. I hope it wasn't too technical. Thanks. Any questions? Yeah?
I think the idea of interferometry based on the broadband flat response of the optical system, and the usual PDH using temperatures that utilizes the steep response as a resonance. Mm-hmm. Is there any hybrid nice idea which can enjoy these features of digital interferometry, while we can have the benefit of the optical response of the cavity.
Absolutely. I think what you could do is you could transfer, in some of the arm length stabilization schemes, you have something that you use an auxiliary laser to get the cavities close to resonance, and then you can kind of transfer the control from one system to the other. So you could I can imagine you could do a similar thing like that, where you could get initial information from your DI, and then just ramp up the gain of the other control system have your PDH do all the controlling from that, like the fine tuning from that point. I think that's not so different from what's been done using a different 532 nanometer laser that they use for and I think is that the current baseline for the stabilization? Oh. Any other questions?
Well, so maybe along the same lines as Craig's question. In the case of, in most of your examples, you're talking about one round trip, two round trip. Of course, in LIGO we have optical cavities, arbitrary numbers of round trips. And then you also showed an example where with digital readout, you could you have over the whole full spectral range, you have a nice clean linear signal. But let's say that cavity is inside of a microscope, inside of a car, and signal inside of the cavity, inside the cavities, and so on. And they're all changing and going into and out of resonance. I presume that nice linear response that we saw from the digital signal changes dramatically every time a power recycling cavity goes and swoops through resonance.
It doesn't. It doesn't have the dependence of being on resonance, and it's because you're getting real-time phase information. I mean, you're getting information at the location of the optic essentially, and
But as it sweeps through resonance, you go from 0, 1, or 2, a small number of bounce of round trips.
I see what you're saying.
A much larger number.
Right. So depending. Right. So depending on what you're trying to lock onto or something, you mean, wouldn't you be even losing your signals? That where you're saying you'd lose your DI signal completely? Because it depends on if you're in, I guess if in your reflection or in transmission, I mean, there would definitely have to be a lot more thought that goes into.
The key is the DI signal is non-resonant, it's a spread spectrum. So it just sees targets of varying reflectivity, it doesn't see resonance.
It's the one height for that space.
It just sees two optics regardless.
Is it an auxiliary laser?
It's an auxiliary laser, but it's not a coherent beam, it's a spread spectrum.
Okay. You're not using the main laser.
Right. Sorry.
So different, same theme, different kind of question. In LISA, of course, you have a problem where spacecraft are moving, so there's a top pushing. In some sense, the proof masses are always separating or moving. You have to worry about that. You have to chirp the frequency of your.
I don't think so. I mean, ideally though, you wouldn't want all of your power going into this PRN modulation, because you're decohering your beam, I guess, and so you would maybe only do a small. Instead of doing a full pi modulation, you would just do a very small percentage to give you similar diagnostics, but without completely ruining your. I don't know. I'd have to think about it some more. But off the top of my head, I don't think so.
It might be sidebands on the main beam. So the main beam, we would track the heterodyne and the Doppler sheet.
You just got a Doppler side thing.
Right.
Any other questions?
In between measurements, you had something like 100 times higher noise.
In which one, sorry?
Either the second or third experiment that you talked about. It's more like 10 instead of 2
Yeah, in the fiber multiplexing one, is that the one? It probably is. So unfortunately, and I didn't overstress this, maybe I'll try to go back. Unfortunately, eventually your code starts becoming your own noise floor, and so you start getting limitations of how well you can distinguish. If you have so many, if you have. This one?
Yeah, so here the frequency noise is really high. This is a 10 megahertz frequency noise.
So this was nothing. This was kind of just free running lasers. Nothing was stabilized or anything. These weren't performed in particularly quiet environments either. I don't even think I think kind of here that you're limited by I don't know, I mean, I guess by 10 hertz you're already close to your picometer level sensitivity, but at low frequencies you always have an issue, I mean, of reaching, in all heterodyne measurements you hardly reach the shot noise. You can, I don't know, if you're usually limited by other technical noises and heterodyne readouts at low frequencies first, be it laser frequency noise, be it environmental, other 1-on-F noise like thermal things.
I was just wondering, are these limited by some fundamental limit of the PRN, or is it just technical?
You're saying kind of at this level?
No,
at this level, no. This would be something else. I mean, like I said, these measurements weren't done in any kind of quiet environment at all. So I imagine it's some environmental noise. At this kind of level, you start getting into your own limit of PRN noise, I guess, of code noise, where you have so many codes that you can only do so much averaging to get rid of all of the non-wanted reflections. Even though you want to pick off multiple signals, you can only average so well to a certain level, and that's usually around at this level with these powers. Cool. Well, thank you very much for coming. And if you have any questions, I'll be around for a while, and I'll be at JPL to the end of the month. So be sure to email me if you have any questions. Thanks so much.